My name is Tai Chen. I'm a student from Troy High School. Um, I am a part of this year's RoboSub team as part of Troy NJROTC. Next year, I'll be the software commander for this team. This year, I've been part of the software team, working on designing and actually executing the software aspects of our AUV. The sensors on our AUV have been chosen to provide the needed information to navigate and position the robot in the correct place, but not provide too much information, as to overload the Jetson Nano with unnecessary data or lead to wasteful battery consumption. We chose to have two sonars, two cameras, and two hydrophones located on the AUV such that the forward-facing camera with horizontal motion could scan the immediate vicinity for the targets, while the rear-facing camera served to align the AUV depth-wise relative to other markers. The two hydrophones face toward the front and back, respectively, to better locate the pinger locations of the last two challenges. Certain objects in the last two challenges will send out pings that can be detected by our hydrophones to guide us through the challenge. As the next challenge could be anywhere after a challenge is completed, only one hydrophone with a 180-degree field of view was not enough. As the AUV will always be facing toward the target object, the forward-facing sonars allow it to better detect the object and understand the immediate landscape in front of it. To review, the confidence our team has in completing each of the respective tasks is as follows. Gate 85%, buoys 90%, fin 70%, torpedo 70%, and octagon 70%. In the first three challenges, vision through our cameras and depth perception through our sonars will be essential. Pingers are not present in the first three challenges, and so our hydrophones will not be used. The forward-facing camera will detect the target via object detection through our machine learning software. To use machine learning software requires extensive computing resources, and that is why we used a Jetson Nano as our CPU, as it comes with a graphical processing unit or GPU. Sonar will be able to pick out the target from the surrounding water, and using these two inputs, the AUV will be guided toward the target for the first three challenges. In the buoy challenge, Vision will have to distinguish between a Tommy gun and a badge to gain us the extra points from touching the right buoy, as determined in the first challenge of the gate. For the bin challenge, camera vision will be used to discern objects to be placed into the bins. In addition, the use of color vision by our team allows us to distinguish the yellow color of the bins to acquire the points from taking off the cover. Again, camera input will be analyzed to distinguish between the two bins. There are four distinct images, one image for each bin will be fully visible. As such, our algorithm has been trained on all four images, as we do not know which two will show up during the competition. The last two remaining challenges, Torpedo and Octagon, allow us to use our hydrophones to detect pings from the targets. The Torpedo challenge will require our AUV to first distinguish what image is on the board. If the image is not of our team's chosen image, the AUV is on the correct side. For example, an AUV that has chosen the G-Man team will shoot through the bootlegger image and vice versa. Once this has been done, the AUV will align itself to larger hole first and attempt that challenge. Later, it will attempt a smaller hole. Our team continued to collaborate online weekly to finalize design choices. At home, team members made the best use of this time and built as much of the AUV as possible, despite not having access to the facilities on campus at Troy High School. In addition, we tested the vision and sonar aspects of our AUV separately, which in hindsight was an efficient use of our time. For vision, we implemented new algorithms to fix and calibrate difficult input in terms of camera input that was too green. Turns out, this was a common problem in the marine robotics industry, and we sought solutions online. Eventually, we implemented an algorithm known as see-through. Our team troubleshot problems with our hydrophones and sonar as well. The disruptive qualities of water resulted in the need for higher operating frequencies than standard for the sonars. The water would distort the sound waves sent out from the sonar, and we would get bad readings. Eventually, we settled on using 115 kilohertz to acquire proper readings from the sonar. The positioning of our sonars on the AV was a problem, and that was resolved with a smarter algorithm to calculate distance to other objects. In addition, we use simple geometry to find distances by comparing values from the two sonars. As the pandemic wanes, we'll be able to fully test our complete AUV better.